Once again, suppose you have a coin with an unknown chance of heads. The frequentist is going to interpret this to mean that the chance of heads is some fixed number p, I just don't know it. It is a nail that has been hammered into the unit interval. I don't know where it's been hammered in, but the nail is fixed, it doesn't move. The Bayesian, on the other hand, will say, I don't know this probability, so I can describe my uncertainty about this probability in terms of a probability distribution. That is, for the Bayesian, the parameter itself is a random variable. And this is a new way for us to look at parameters, and it is extremely versatile and extremely powerful. So what does this mean? It means that the Bayesian is imagining that here's your interval 0 to 1, and of course there is no probability outside, sorry, there is no probability here and there is no probability here. But somehow a coin is being picked at random in the unit interval, and the Bayesian is prepared to put a density on the unit interval. And today we're going to put ourselves in the shoes of the Bayesian who says, I don't know anything. I don't know anything about this coin, and so I'm just going to assume that the density is uniform. And so this Bayesian is assuming that the goddess of chance has thrown a dart on this unit interval, and wherever that has landed, that is the P of the coin. And the dart is completely uniform on the interval. This is before the data, and so it is called the prior density. Of what? I'm going to call it X, and X is the random chance of heads. And so the prior density that this particular Bayesian is using is uniform on 0 to 1, which for future reference, I'll remind you, is also beta 1, 1. And that's fine. That's what they think about the coin. But then, suppose we run the experiment. So you pick a coin and you toss it. And you toss it n times. And the natural thing is to count the number of heads. And so the number of heads is random. And I'm going to say the number of heads is h, because I've called x the p of the coin. So I started out assuming that I don't know anything about this coin, but now supposing I toss it 10 times and I see 9 heads, then my opinion is going to change. Now I'm going to want to say, no, this coin is biased towards heads. I don't want a uniform distribution anymore. I want to push the mass of the distribution towards the high end of the interval. And so we're going to try to formalize how to do this. And so what we do know is that if we know P, then the distribution of H is binomial. And so now this is a conditional distribution given that the value picked for the coin was P. The conditional distribution of H is binomial. And that's fine, but what we want to know is, given H, what do we now think of the coin? And so we have to update our opinion. Given that there were K heads, what is the density of this random probability X? This density, which is calculated after we see the data, is called the posterior density. Of X. And so let us start noticing some language here. So we have the prior density, that is before the data, that's our opinion of the coin before the data. And then there's the posterior density, which is our opinion of the coin after we have seen the data. And so what we want is the density of X given that I saw K heads. And this is a density on 0 to 1. Well, actually, yeah, okay. If you want, you can do that. It's fine. So in order to find this, we can notice that we just go to first principles. This density, we're just reminding ourselves of what's given. PdP is the chance that X is just around little p, given that H is equal to K. And so now we have to try and figure out what that is. And we have the division rule, or Bayes rule. So X had to be around dP and H had to be K. And this probability we'll take relative to the chance that of what is given. That is the chance that H is equal to K. So let us look at the numerator. Remember that X, to start out with, is uniform on 0, 1. So it is natural to split up this numerator into, okay, then X had to be around, X had to be in dP, and then H had to be K, given that X was just around P, and then we have to divide by the overall probability that H is equal to K. Now the denominator is actually looking like the best of all because the denominator does not have a P in it. So as far as this density is concerned, which is after all a density on P in the unit interval, as far as that density is concerned, the denominator is a constant. There's no P. The numerator, let's try and work out what the numerator is. And so that's a 1 dP, the first term, the chance that X is in dP because of uniform. And now, given that your coin landed heads with chance just around P, the chance of getting K heads is binomial. And we'll have more to say about that X in dP versus X equals P later, but for now, let's just go with the binomial probability. You will remember from an earlier discussion of conditioning on a continuous variable that saying that X is equal to P is essentially the same as giving the condition that X is in dP. Okay, so that's the numerator, and then you notice that I'm just refusing to calculate the denominator. Why? Because I'm trying to find a density, and the variable is P, when there is no p in some part of the density, then that part must be in the constant that makes the density integrate to 1. So I'm going to ignore all of the constants. I'm just going to call the whole lot C, and I will have a p to the k 1 minus p to the n minus k dp. And so where did I start? I started here, and here was my density dp. This is what I'm trying to find, and I have all of this. And so what I know now is that my posterior density, given the data that I got k heads in n tosses at p, is some constant times a p to the k times a 1 minus p to the n minus k, and that sure looks like a beta. And this is beta k plus 1 and n minus k plus 1. And so what we have shown is that if you start with the uniform prior and you observe k heads out of n tosses, then your posterior density is also a beta. It's just that the parameters have changed. And exactly how have the parameters changed? I'll just make a note that this is the posterior here. And so if we look at our prior, it was the uniform, so it was beta 1, 1. And the posterior is beta k plus 1 and n minus k plus 1. And so let's find all these ones. My prior beta rs, the r was 1. That 1 has been transferred down to our posterior. And for the posterior r, I have my original 1 plus the number of heads. And for the posterior s, I have my original 1 plus the number of tails. And that's a very easy way to update your opinion about the P of a coin. You start out with a uniform prior and you just keep adding the numbers of heads and the numbers of tails you see and to your beta. So does this actually make sense? Well, what is the posterior expectation? The mean of a beta RS is R over R plus S, and so it's K plus 1 over N plus 2, which is for large N approximately And so you see that initially your prior distribution had its mean at a half. So you had no information and you said, okay, I expect this P to be a half. But now you have tossed coins, you have gotten data, and now your posterior mean is getting pretty close to the actual observed proportion of heads if your sample size is large.